Yeah, so this is actually a kind of experiment I am doing because I am trying to teach particle physics and there are high school students here. I'm most of them high school students. Yeah, let's see how it goes. It's like this baby quantum mechanics book, na? We can teach particle physics to high school students. Don't get scared. This is the last slide also, okay? This is the last slide. This is what is coming. So we just go through what's in here. So these parts just ignore. That is what we are going to do. This you just look at it. So in the standard model we have the fundamental particles. We have quarks, which comes in 3 flavors, 6 flavors, and like up and down charge strength, top bottom. And we have electrons, which are electrons and neutrinos. And we have the force carriers bosons, which is the W plus or minus, this is plus or minus for the 2 W's, Z, the photon and the gluon. So you probably are familiar with, or hopefully are familiar with photon, I guess. Like photoelectric effect is the, we get the concept of photon. And the, how does this work? Yeah. So this is the Higgs particle, which is my baiting thing, Gautham particle. So yeah, we will see how. So just get an idea of what are the particles because we will be using these particles in the coming days like freely. So there are leptons, quarks, the force boson and the Higgs boson. And so there was a talk on the hadrons where you guys saw what the quarks were. Yeah, so I'll begin with the simple prereq concepts we need to understand the talk. So one is the concept of Lagrangian. So in classical mechanics we usually define the Lagrangian as the T, which is the kinetic energy minus the potential energy. So it is a, like we can look at it mathematically. So as a function, this is called the, this is a functional of Lagrangian, which gives the, which on, this is something called variational derivative, which is variation with respect to the variables. We put 0. This is called the action principle. If you have to get the laws of motion, like Newton's laws of motion or any laws of motion, what we do is we extremize or put the delta as 0 for the corresponding Lagrangian of the system, the action of the system. Yeah, so doing this under some boundary condition, which are like it goes, it decay in the boundary and some assumptions, we will get the Euler Lagrange equations. So this takes the form of the laws of motion. These are the, but when I refer to laws of motion, I usually will be mentioning this. Now this is Lagrangian. Now there is a concept of Lagrangian density where we write the Lagrangian as a spatial integral of a function. So if we can write like does not always exist. If it exists, we call this the Lagrangian density. Usual density, you integrate density, you get the Lagrangian. And we'll look at an example. For example, if you have a Newtonian gravitational potential, if we will get the Lagrangian, which is kinetic energy half mv square minus of gmm by r. So if you look at the Euler Lagrange equation, we get the force is the Newton's law minus gmm by r square. So this is how it comes in classical mechanics, and in a way in quantum mechanics also. And in quantum mechanics, the states of a system is described by what is called the wave function. So states are elements of a Hilbert space. So it's a vector space with some additional structure, and the probability for something, like we have a probability to find a system in a definite state. For example, we need the electron in the ground state or in the state n is equal to 2. It will be given by the norm squared of the wave function. L square. L square is the Hilbert space. It's a square integrable function. The space of square integrable function. What does the L stand for? Do you remember? Right. Yeah, and also in quantum mechanics, the wave function satisfies the Schrodinger equation. And the Hamiltonian this is something called Hamiltonian, which is kind of like Lagrangian but a little different. It is given by, the Q and P's are like space and momentum. And this will be given like this. So if, for example, usually we had we had Lagrange would be t minus v. Here it will be like usually it will be t plus v. So especially in quantum theory, this gives an idea of what energy is. Yeah. Now, this is a notation. This is follows. So many mathematicians do get race baited by this, right? The mathematicians usually get race baited by the race. Yeah. So we define what is called a 4 vector. 4 vector is a 4 component. It has 4 components: time and 3 space components. And we will. It's not just that they have a transformation property. They transform according to the suppose. So they transform according to a specific transformation called the Lorentz transformation. So, and the actual convention coming here is, so when Einstein was using this to do general relativity, he was tired of putting all the summation signs everywhere because there will be like 10 summation in the equation. So what he did is, whenever something is repeated like up and below, then we are assuming it is summed over all the indices. Okay, so this is very important. Okay, we'll be using it in every single slide. So is everyone fine with the convention? Okay, good. Anyone race baited by the convention? Of course. Yeah. Now we are getting into quantum field theory. Yeah. What I beginning? We started with Lagrangian. We in what minutes? 5-10 minutes. We reached the QFT. Okay. First of all, I have to tell. My aim is not to teach you QFT. Okay. What I am doing is I am showing you what are the things, especially the math inside the particle physics, like which was actually my motivation to study all of this. Like getting into the state to even reach here is very hard. So we need good motivation to reach there. My motivation was knowing all of the things, or at least having an idea of all of the things that is going to come in the coming slides. So my aim is to just know this is what happens, this is how the math looks. That's it. And especially this public is, I know it's not a public where if you see complex math, they won't hate it, they love it. Yeah, so we will define what is called the S matrix or the scattering matrix. So consider two states. The particle physics is about scattering two particles. So some particles come like here, they scatter, they go to the out states. So there are in states which comes and out state which goes in the basic idea. So what do you want to know? So suppose we send some in particles, what will be the out particles we getting? With what probability? What will be the probability of getting each out particle? So that is defined by this inner product. So this is like, we know taking projection or dot product, we know how it is if we have like the idea of projection. So here we get the amplitude which on square gives the probability. The probability amplitude will be the inner product of the plus denotes the in states and minus denotes the out states. Yeah, so this represents the probability amplitude for the alpha state to go to the beta state. Please ask me the doubt. I know this is a complex topic, especially for you guys. So please ask any doubt you have.
What is the P symbol?
P symbol, momentum. It is the 4 momentum. 4 momentum is the time is energy and other are the momentum. But here actually it's not mv, it will be actually gamma times mv, where gamma is called the Lorentz factor 1 by root of 1 minus v square by c square. Okay, so this is the Lorentz factor. So the momentum will be gamma mc square and gamma p. This is the usual classical. I shouldn't do this. Yeah, this will be the momentum. This is a 4 momentum. This is the first component. This is the other space component. Yeah. Gamma
MC.
C is equal to S. Yeah. So yeah, I will be putting C is equal to 1. Obviously, yeah, we can't put pi is equal to 1. I really want to put pi is equal to 1. Now, This is just I'm mentioning this because this will be what we'll be actually using in a computation, because this corresponds to this states coming, going without doing anything. So we are not interested in that part. So we separate the other part, which is the M, which we call the invariant amplitude, and the other one is also invariant amplitude. So we call this the invariant amplitude, which will be, I mean, in this slide you are not going to see it, but whenever you are doing particle physics, you usually encounter this more than the symmetrics.
So basically we get the invariant amplitude by just solving this out.
Yeah. Like we will get a form, like when we solve for symmetry, we will get a form like this, with a delta function, like a term like this and a delta function.
Delta to the power 4 is?
Oh, good question. I didn't mention about the delta. So this is something called the Dirac delta function. It's actually not a function, it's something called a generalized function. So one idea to look at is like, you know the Gaussian curve. So suppose you fix the area under the curve and you take the width goes to 0. So this gives something like some graph like this. This is what delta function is. It has the property, or by definition it is a function such that minus infinity to infinity so if you integrate it with a function, smooth, whatever, like I'm not asking smoothness, everything that mathematicians care about physics don't much. So if you integrate, especially this is from some minus k2 plus k, like this integral should have 0 in it. Not 0 only. This 0 of this thing. So if you integrate with something like this, why am I doing this? Yeah, if you do this, you get a force 0. If this integral has 0 in it. So this is what delta function. You multiply with any function, you integrate it, you get the value of the 0.
Why are you powering it by 4?
It is because it is actually what happens. So delta power 4 or delta power 3 is, here P has 4 terms, right? P has 4 terms.
Yes.
So it is delta of P0 minus P beta 0 minus P alpha 0, delta of P beta 1 minus P alpha 1, the product of these. This is a product of 4 matrices, like the power 4 in the little b. Yeah, I think so. Now we are going to get into real business. Get ready. What? Okay, I know this looks scary, but this is very beautiful.
No, I will not sleep.
Huh?
I will not sleep.
Yeah, I'm saying we started with a scary looking Lagrangian and a gauge group. We have to get this is, we will see how it goes. Yeah. Anyway, this is very beautiful. So if you consider, so here, so look at our bus beta is the outstage. So suppose we have some many particles. These are the many particles outstage. Okay, these are the many particles coming inside. Why am I? So these are the particles that is coming inside, and that's these are the particles that comes outside. So we want the general expression for this. So by doing many things, you do Dyson series expansion, something like it's like a Taylor expansion on the powers of H, which is the interaction Hamiltonian here, and you do many things like the time. Okay, the time order product. What is this? Is this orient the Hamiltonian in a time order?
It's okay.
Guys, so what the time ordering operator does is this all have time, right? This is some x01, x11, x21. So these all have time arguments. So what this operator does is this just organize them in the time order. So like we have to first, the things that happen first should happen first. Things happen after that should happen after. That's it, what the function is. So we get this, and there are other terms which are actual terms. So psi 0, the psi zeros are just the vacuum state, nothing state. Okay, vacuum state. These are vacuum state. it doesn't have any particles or anything inside it. So now the important part of this expression is A dagger. So what A dagger is called the creation operator. So what A dagger is, suppose I have a vacuum state. Now I act on this vacuum state by the creation operator of, let's say, electron. Okay, with some momentum specified whatever. Now what will I get? I will get a state with an electron. Okay? Is it fine? Please ask questions. A dagger is listening on. A dagger is a operator which acts on the vacuum state and gives the whatever it created. Like it's creating a particle. It's creating the particle.
Why is that minus I to the n by n factorial?
Oh, that's coming because it's a combinatorial factor in the derivation. Like all the possible way to tell.
Oh, okay. Minus I?
Huh?
Minus I to the n part.
It is there in, how will I say? It comes from the definition inverse, it comes like there is a factor. Like the definition of fields, it comes.
So it is,
Yeah. You know the name, vacuum state?
why is it converging?
Good question. It's one of the hardest things in physics to make it converge. We assume it converges. Actually, there is a lot more work called renormalization to make it converge, which I am not going to do, which takes days to converge. Like, it will converge. Like, if it is not converge, we will call it a non-renormalizable theory, but we work with renormalizable theory. Or if we have non-renormalizable theory, we will somehow try to make it so that it converges. Okay?
Whatever, wait, means we do, like, are we being renormalizable theory or not physically possible?
Yeah,
or are physically unlikely?
QED, QCD, everything is renormalizable.
Oh,
QCD is very hard. Like, it's not directly
renormalizable.
renormalizable in the sense. QED is, okay, QED was developed in, I think, 1930s, 40s, something like that. And it took decades to make it renormalizable.
Okay.
ED or ED?
Huh? QED, electrodynamics. QCD is another problem, it's very hard.
Oh, so basically.
I'm still not arguing, like, is it complete? I'm not sure. Like, there are ways to deal with it. Like he mentioned, lattice theory, we cannot do perturbation, non-perturbative methods. So something like that we use. But this is for the other parts. Yeah, Baba. Yeah. So the Hamiltonian, we split it in terms like this is a polynomial in the fields. Like there are many fields. There are electron fields, there are mu fields, there are quartz fields. There are many fields. So this will be a polynomial in those fields, where j's are just the coefficients. So suppose a term will be looking like some, let's say, electron. It may look something like this, okay?
What do you mean by field? When I hear field, I think addition, multiplication, subtraction.
Oh, this is the field, like the other field, calculus field.
Robotically gasped.
Okay. You get it? Okay, they are operators. In quantum field theory, fields are operators which act on states and give states. They are not, all operators are not like, for example, we cannot directly call this a field, but some combination of this will be fields, which we will come in. Oh, it's here only. This is a field. Like this combination of A and A dagger is a field, where you and we have some functions satisfying some equations. The equation.
What is the field? Like, how do I tell you something is the field?
Here it's an operator. It takes it's a value. Like it takes an x input and it's a operator which acts on, like this can act on some state.
Yeah.
And it gives some result,
Yeah.
which is another state.
Yeah.
So it's an operator.
But
It's an operator value function.
yeah.
For now, yeah. Like, there are other constraints, but it's an operator value function.
Okay. So all operator value functions are fields.
No, all fields are operator value.
And what is the operator value function?
Like it's related to the representation of the law. Like
I think Piyush has an answer. Piyush.
See, the point is, you say it's a field because it acts on a vector and sends it to a vector. So it's a
No, I'm saying not all of them are fields.
Not all of them.
What
are
happens is
fields,
that, okay, the thing is, all the particles, all the fields, what I call is some representation of the Lorentz group. Lorentz group is a group with these transformation. I mentioned some transformation, which like the usual, the gamma, minus beta, gamma,
Yeah,
the relativity.
that
So
is-
they form a group.
Yes.
These are the representation, different representation of the group.
Okay.
And now, then like you have to get to a representation group, which I don't want to get into.
Okay.
Like they are different, mostly irreducible representation of the Lorentz group.
Okay.
Yeah. Like we can write them in this form.
Okay.
For now, what we call field is of this form. Yeah, so we will have interaction Hamiltonian from some kind like this. Yeah, so okay, so this is creation operator. So we were here. This is creation operator. Okay. I don't have that space in the board. This is so now the A without the dagger is the opposite of it. It's a destruction operator. It's an annihilation operator. So suppose I have A which annihilate the electron from the electron field, it will be some coefficient times the vacuum. Now if I try to annihilate anything from the vacuum, I get 0 because you cannot destroy something that does not exist in the system. Logically, like that's actually the definition of the vacuum state. Vacuum state does not have momentum or anything. From that definition, it follows.
So, like A dagger is identity.
A dagger is not right.
It's not one.
Huh?
A dagger is identity.
What?
A dagger is identity. A dagger is
Both of
identity.
them are not identical.
Huh?
Like they have some. Like they don't come in.
No, okay, they don't come in finally.
If they are I, then I minus I 0. Okay, I think I have.
So if I
Yeah, that's a computation.
Okay.
Okay, I will tell you what. So everyone knows what a commutator is. Here the minus negative sign is a usual commutator. Commutator is of AB is just AB minus BA. Okay. So the plus corresponds to something like anti-commutator, which is AB plus BA. That is just there because you guys have heard bosons and fermions. So if both of those particles are fermions, this will be plus anti-commutator. Otherwise, it's normal commutator. Okay, we can just look at the boson side. Commutator is this.
you go back and explain.
Oh, what?
Yeah, continue.
Yeah, continue. Guys, please ask every question you have. Okay. Yeah.
Why are we destroying the primed part? Don't we have to create them because they are?
I will come to the rule. Okay, so you understand what is creation operator, destruction operator? Yeah.
Like when you say like that phi 0 and phi are like fields,
Yeah.
like so like does it represent like when you say phi
It's okay. It is related. It's kind of related to a wave function. In the sense, suppose you have a okay, this is very heuristic argument. Suppose you take the inner product with something called x, which is just a delta function, and the field and the vacuum state. You can say heuristically you get the wave function we are familiar in Q. That is no longer like this acts on the vector, so it's no longer an operator. This is a function, not an operator. Value. It's a complex value function.
like, so does the electron have like a position or like
Electron does not have. They are fields. Like in QFT, there are no particle. There are the only constructive fields. It's like okay, the conceptually, even the pop science thing we can imagine that. Like the world is filled with some space, many fields. Electron field for every particle there are fields. So there will be excitations on the field, which coming due to these operators, the field operators, the field field. So those correspond to the particle. Those excitations have momentum and mode, and when a lot of them are there, we effectively see it as particles.
but like even the excitations will have some like positions, momentum.
I'm saying no. At each position and momentum, there is a definite probability to find them. Like there may be a place with very high probability.
It's a probability or probability density.
Probability density.
And so like no like what I mean is we apply like a creation operator to phi 0 like so it's like an electron that is like everywhere equal probability. Like,
Sorry. Okay, so this is there is. Now it's clear.
yeah.
Like at some place I'll be writing this. I'm just explaining. That fields are function of the space and time. They have a definite value at everywhere in the universe.
So fields basically tell us how to change this thingy to also include the electron. Like if I say a field of electrons, like an electron field, it basically converts the space of the state of the universe into one which also has electrons.
Yes.
Okay.
A field creates an electron. Like the electron field creates an electron.
Okay, that makes sense.
Or a positron destroys the electron or create a positron.
That makes sense.
You guys are familiar with the concept of antiparticle? Electron, positron. Yeah, that's good enough.
Are the fields themselves quantized?
Yeah, we are talking about quantum. It's a quantum field theory. This is their quantized and something called second property. Like again, I'm not trying to teach you every single thing, every single detail. There are some like once you after this we will go to something called gauge theory, which is the very mathematically also interesting part. Many people here research about this, me, and maybe more people here.
Nobody is here,
Huh?
Nobody is here.
Yeah, I'm saying this close.
No, I'm just thinking you could probably mention this.
Yeah, so we understood what is creation and destruction operators, right? They have values which acting on states give those states. Okay. Yeah. Now, so now let us look at this equation. So what does this does? So here, for now, understand the inner product as just the product of these. Some kind of product. So what we does here? So we are just looking at this concept. This is some combinatorial parts and integration of the polar space. That some primitives. Now this is what we are worried about, which looks nasty to you. So what happens? We have a vacuum state. So what is our process? There is some board here. So some particles come which are the non-prime particles. Like I am using prime for outgoing and non-prime for incoming. So some particles coming, some particles going. We know which particle, like we are understanding of what particle, like we are fixing what particle come out, what particle go come in. We are fixing that. We want to know the mode of that, so we know that. So what happens is, first we have the vacuum state. So okay, think about it like this. There is a collider here. Okay? Here we accelerated stuff. We get from here we outside we get it to the detector. So here we are sending the in state. So what does, so now this equation works inside the collider. So inside the collider what happens is, there is nothing, there is vacuum inside the collider initially. Now the in state comes. So what does this does? This creates all the in states. A dagger creates. Don't confuse with that, A dagger creates. A and helix. Even in the beginning I also used to confuse a dot. A dagger creates. Like I remember it in the sense what I think it is true is wrong. That's how I remember it. I know why this choice was made like okay, there are races in even quantum mechanics. Like there is some versions in quantum mechanics oscillators. Yeah, so there is a dagger which creates some particles, the in particles. So from here we have what? The in particle. So here it is in particle. Now this is in some time order coming from first happened, second happened, third happened, fourth happened, up to eighth happened. Now the first Hamiltonian does what? Some of the Hamiltonian contains this HIs contains, for example, this contains the information that these three interact. Okay, or some of this interact and we get some other process. So the Hamiltonian encodes the idea of the interaction. It makes the fields interact. So here we have some states. Now the Hamiltonian, the first Hamiltonian in time, first does it interaction. The Hamiltonian interacts. The first Hamiltonian, here will be some HI will be here. Okay.
What is Xn?
Huh?
Xn?
Come on. this is a perturbative series.
Right.
We are perturbating on the number of Hamiltonians.
Okay.
The more Hamiltonian there is, like there are more so these coupling constants are usually small.
Yeah.
So we are perturbating on the degree of the coupling constant.
What is Xn?
Xn, like I'm saying, it's an integrating variable. They are four vectors. Space four vectors.
Space for.
But whenever you see x1 or whatever this, it will be space over. X will be for x space over. Some place will be 3, but it will be clear from this being 3.
Okay.
Okay. Yeah. So what happens is the first Hamiltonian interacts. So we have some incoming particles. The Hamiltonian interact do something. It creates a new state.
Okay.
Because the Hamiltonian interact with the in state. Now there is a new state, which is maybe different from the in state. Goes the next Hamiltonian. So n Hamiltonian interactions happens.
But isn't Hamiltonian just energy?
Huh?
Isn't Hamiltonian?
Hamiltonian has the operator. Here Hamiltonian act on the field and give field.
Okay. So Hamiltonian is like the transformation, time evolution thinking.
Yeah, it's a time evolution.
Okay.
It's not like time evolution is something called exponential Hamiltonian, but
Yeah, right.
okay.
Instantaneous time evolution basically.
Yeah.
Kind of.
In idea, it's
Yeah.
in language you can say
Yeah. Yeah.
time evolution.
Okay.
So it goes, but is it clear, guys? Everybody? So states comes, Hamiltonian make them interact. There are a lot of Hamiltonians. Then we have some another states. Now this want to get out to the detector, which means inside the collider these are getting annihilated. So these particles annihilate all the particles which were created, which were outgoing particles, and make them into the detectors. So this is what the term means. So first we had the vacuum state inside the collider. We create the in states. We does the time evolution. We destroy them.
Okay.
Now this interpret is just to get the properties.
Yeah. Is it possible that something left like your remnants don't have like it never happens with their remnants after the interaction?
No, after interacting, every field is included in here. Whatever particles come out is
When something does not, it doesn't happen and something just stays there.
saying that also we consider. You say heuristic argument. It's not
Okay.
everything that is after that we call them outs.
Okay.
It's not they have to go to from here to there.
Okay.
Like what are those steps? That is what called as out states. Like this actually happened. This happened like literally. Like this. So you understand what the series is. So initially I know this looked very scary. It's that scary now. You guys have an idea why this term is there. Other is just combinatorial fact. Does not matter. This clear? Doubts? Okay.
Why minus I over I and it doesn't make any difference.
No. Yeah.
Minus I versus I can't be just in a
It's a relative sign anyway. Like you have to put some sign. Sorry. Like this comes from the definition we did already for. Okay.
How did it come?
It's come from like the field like from here.
Yeah.
Like there are terms here, right? Or in a say like how will I say how I terms come? Those comes. Like the derivation of this like takes a lot of time. There are many theorems using, especially something called Higgs theorem. It's a very important theorem. I'm not mentioning it here. So you do many stuff. You use the commutative relations, how the time operator like terms on how you exchange stuff. All these produce so many factors which are those. Now, have you guys seen the fancy diagrams, Feynman diagrams? You see some particles coming, some coming out. This is doing it even in movie, science fiction, you will see people drawing diagrams, right? Like diagrams like this.
I saw in category B.
Good. Yes, it. Everyone is familiar with this, at least how seen these kind of diagrams. These diagrams are these terms. All the diagrams correspond to these terms. Okay. So, yeah, so we looked at the Hamiltonian. Now we have the fields. The fields will be some, okay. The U is the coefficient of the annihilation operator. V is the coefficient of the creator operator with some exponential factor. This is just the space translation. What this does is translating space. Also, there is a time component also. So in space time it goes. So this is what, so this u and v will now come out. This psi, v, u, everything will come out. This should be clear what we mean by it. A field will be written in this form. And I can mention I sometimes split it into this and this separately. Because this is one corresponds to the particle and antiparticle. So the L, whenever I use something like L in the field, it represents the what is the particle, like say the electron spin, like it represents the particle type, and like I told you the fields are coming from the irreducible representation of the Lorentz group, and it has some data about the mass, some component, what representation it is, things like this. Yeah, so now we will learn to draw these diagrams and we will see how to calculate. So writing this and calculating it is not easy. So we want to some intuitional way to write these terms, calculate these terms by drawing diagrams. So for that, what we have is a Feynman diagram will consist of vertices which correspond to each of the HIs. Each of the HIs, each of the monomers in the Hamiltonians corresponds to a vertex. What is called a vertex, which will be a dot with things outside it. A vertex, geometric vertex. And it will have lines representing. So this kind of ignore it. This comes from my computation, like those computation relations. Okay, we can say it. It's a creation of annihilation operator. What it does is create an operator, make it go, annihilate it at the vertex, or for antiparticle the other way.
How does creating a particle then remove it not to nothing?
No, it create, it goes under some evolution. Then
I'm saying in the first one, just the first one. A, B dash.
first of all, those are different. No, first of all, if they are two different things, they do come out. They are two different particles, but the same particle, there are other terms. Like it's not literally, like there are some other coefficients whenever you destroy it. How will I say this? So it's not like on the vacuum we on the vacuum it's fine. Suppose on the other some other fields, there are already some existing field. When you create on it, it is fine. But when you destroy it, what you get is not a single state but a linear combination. A linear combination of them with some sign and some combinatorial factors. That is what you can say. It's an operator, the operator has no summation relation. You look at the derivation.
Why does it have this computer relationship? What is
It comes from when you derive it.
equation? Is that the two very simple like
Again, you give it intuition for the computation. If they are two different, like suppose if they are something completely different, there is a commute.
yes.
Okay.
Because you add remove from different place something like that.
Yeah, they are not dependent.
Yeah, that-
But if you are doing it on the same thing, it depends upon if their momentum is same. This means the moment, like whenever you use something inside the delta, it means they should be equal.
Yes.
So it means the momentum should be same. The sigma, the spin, sigma is the spin of the particle. The spin should be same, and the particle species should be same. So if all of them are same, then they don't come into it.
Then why did they, isn't that just very, why is it, I said I don't compute that, but why is this specific value, like why is it just differentiation? I mean it's not infinity, but
I mean, I can show you the derivation after. Yeah, individual, I don't know if I can give for this. Does this make any sense? Creating and destroying is equal to you destroy, create. Nah, it doesn't make sense. Yeah, sorry for that. I will talk with you later. After. Yeah, so the lines here represent the particle. So if a particle is moving, the lines will have an arrow on the moving direction. Okay. So like if a particle is going, suppose it is going from one way, so here, suppose it is coming from here to here, it will have arrow like this. Okay. And if it's an anti-particle that's coming from here to here, it will have an arrow like this, opposite arrow. We will say anti-particles travel backwards in time. Whenever you hear that, this is what it means. It's not like really take up physical. Okay, this comes from this sign difference. The particle and antiparticle has a sign difference. Initially, when Dirac proposed it, it was thought as negative mass. But then people understood, because two things can happen, right? Here the coordinates can be minus, or the mass can be minus in the moment.
Can't it also be some competition like mass is
No,
multiplied by I?
No, you will see this. If you in quantum mechanics itself, you will see.
Okay, so it's always only one thing in this.
Yeah. You cannot. There's some like you cannot say mass is minus.
No, I can find mass I. But like multiply mass.
No, I'm just saying. I'm interpreting. I'm interpreting that negative sign as going in the backward direction.
Okay.
Okay. Yeah. Now, if suppose there is something like this, which this is a vertex, this is a vertex, the both end of this line is connected to the vertex. If something is like that, then we will call it an internal line. It corresponds to something that happens inside, which is not in the in or out state. Something that is not internal lines or external lines. There are two kinds of the in states, out states. So I will call initial internal lines, external lines, final external lines, and internal lines. Now we will see how to calculate the symmetries in a perturbative. Now we want we are doing it in each order. So what we will do is, so we are calculating something of order ni in each of the his. Some of them may be 0, some may be 1, 2, 3, more computer sucks. Now drawing, so let's see how to draw the diagrams. So first we create ni vertices of type I. Like all the, according to how many fields are there is all these Hamiltonian terms which are vertices have some properties. Suppose they have 3 lines, suppose they have 4 lines, and each of these lines should be some specific particle. So we draw the vertices. So now we are getting into the Feynman diagrams. So we draw the vertices corresponding to nice. Now, okay, so the convention I am using here is from time is like this, which is usually, okay, I think I should okay, I am mentioning that convention, but I will take upward should be considered right and downward should be considered left. It's better to draw it in. Yeah, so if something is coming from the left, which they are the initial state. The initial state comes from the left. The same way, from here, we are sending the particles. So we are sending them, suppose they are come to this vertex. Okay. Now, similarly for the out states. Now, these internal lines like this are the criteria, let's say, to have 2 of type A, 2 of type A, like the Hamiltonian HI corresponding will have a property like the state 2 of type A coming and 2 of type A and 1 of type B. Okay, so and this will be B. So this both has B, so we will just connect them. So you draw diagrams like this. Like we will see what are the diagrams like. At the end, when you consider electrodynamics, chromodynamics, you will see what are the diagrams they create. What are the vertices they create. So this is how you draw a diagram. You can show all the vertices, connecting lines appropriately. Now, yeah, you will say this is an interaction of type I, this is a kind of interaction of type J. This is calling the means. And now, suppose, yeah, so this had A and A. So at this end I label it A. At this end I label it B. At this end I label it B. A, C, C. So in a vertex I label it them like this. Whenever a vertex is there, the ends I label with the field type. Now for the free ends, which are the in and out state ends, for them I just, because we are sending particles of a definite momentum. Okay, you come, is there a definite momentum? There is no. Like when you do actual things, you approximate by ways, like packets and all, but this is the answer. So these will have some momentum, P2, P1, some spin species, some primes here. Okay, this is how you draw. Now that drawing is complete. Sorry, drawing is not complete. For the internal lines, we will denote the momentum by Q. This is something called off-mass shell momentum, which means usually the momentum satisfies the equation, this equation. This equation. P square is just P mu minus m square, negative of the mass square. The norm of the momentum operator is the mass connected to mass radius. Okay, that's special related link. You have the equations P square C square plus. You have seen the equation. So this is the. So P square is minus m square. So all of these satisfies those equations. But when for the internal lines, I am giving a Q which is a off mass shell. That means this is not satisfied. Q can be even negative, positive, whatever. Q square can be negative, positive, whatever. They integrate through all of the values, minus infinity to infinity. And the direction of the momentum will be the direction of the arrow. If there is no direction of the arrow, then it doesn't matter. Now, how will we get these terms from the diagram? That's what we are looking at. Now we are going to draw a diagram. Doubts. This is getting insanely boring.
What about the lines? Doesn't the lines matter? Like, let us say in 3D you would have 3 points which like just avoid each other. But in 3D, you would have certain shapes which are possible which are not possible.
You will do something like this. How do you draw something?
Yeah, so you do like this.
You draw it like that. It's understood. You usually keep it like this.
So you can.
This is a like this is a illusion. It's a trick. Feynman trick.
So you can make particles pass through particles.
Huh?
And can particles pass through particles in 3D?
What do you mean? This is a diagram. This is just an intuitive way to think what happened. This is not what actually happened. Actually, some fields are there interacting some way. This is just an intuitive way to look at this. Do you really want to compute all of these terms each day? That's actually what we are doing, but getting the terms is better like this. Okay, I don't think this will get. Like, I haven't even started the. Okay, this is the boring part of the seminar. The interesting part, Daniel's theory, Higgs mechanism, all comes different. I don't know if I get the time to do it. If you guys are interested, we can go more.
This is last also can extend.
Okay. If you guys are, if I'm not getting bored, I'd like to extend it. Yeah. If you feel like it's boring, you can give. Chirayu, sorry. Huh? No, there is something after this.
I mean, how much time will it
Board
take?
means.
It should take at least half an hour.
Half an hour.
Yeah. At least.
Yeah.
Yeah. So, did I mention it? Yeah, here I mentioned. So now how will we have diagrams? Now how will we get the rules? So every vertex gives a factor minus I. Actually I write this. It is here. Every factor gives a factor like this. So this is just a coefficient, the coupling constant. For example, E square, something like that. Now some I pi factors, doesn't matter. And a delta function. And look at this. What is this? This is just saying momentum is conserved at the vertex. This is saying momentum is conserved at the vertex. This is the incoming momentum. This is equal to the outgoing momentum. It's a simple fact. You have a delta function with momentum conservation and a coefficient which is the coupling constant, which we know. So every vertex, so this vertex will have such a form, this vertex will have such a form. Now, suppose an arrow is upwards, means in this direction, say, in right is upwards, like for drawing a window. So suppose I have an arrow like this, which is a final extent, so something in here. Okay, so for these things, I add a term UL star by some factor like. Here I stamped a VL. Remember what are the UL, VL? These coefficients or the annihilation and creation operators. Yeah, so for things going out, I will like if the arrow direction is that side, it is like for particles it is UL star, for antiparticles it will be VL. Now for the incoming state, for the for the antiparticle will be, for the particles it will be UL, and the antiparticle it will be VL star. Okay, so you have some vertex term here, some other term V and U here. You have a product like this.
Isn't UL the removal thingy? Isn't UL the removing thingy? The thing which removes annihilator.
I don't know.
Isn't UL the annihilator?
U is the coefficient of the annihilator.
Yes.
The annihilator is encoded in, like, it's already encoded in the, like the annihilator doesn't come because of the commuter relation. Here there is no annihilator.
Okay. Oh, annihilator minus I've got it.
Okay. Like that, in a Hamiltonian there will be an annihilator that pairs with the corresponding annihilator in the field. That's what actions each vertex. So now we have the internal length, which is, this is just formula, okay? When I don't remember this, just I just go to some book and take these factors. This is something called the propagator, or in specific Fourier transform of it, something called propagator. We just say how it moves free. This is how a particle moves free.
Why did it put this? Can you explain a bit?
Oh, I don't think I can. Have you seen something called Feynman
Feynman what?
propagator?
Like the, I understand the summation signal part, you're basically saying you're removing and then you're creating.
Yeah, what this shows is what happens inside. Like you have some particles coming, you have some particles going. We know what happens up to this. Up to here we know, up to here we know. Now we want this goes freely. Na? While goes freely, this is the wave. Let's say like this is the wave function. This is something called propagator. Like this, how propagate the name. This is how it propagates. This has some other form. Okay, this is the final form of it. This the definition is not this.
But if that is Q, then why is this two waves? Like in the top one, you're given. I find out. In the top problem, P and K only takes one variable. But at the bottom one, I think P and K.
Oh, this is a 4 vector. This is 3 vector.
Oh.
This is 3 vector and the time component.
Okay.
I'm just explicitly showing because the n comes here.
Okay.
It's something called a Fourier transform.
Okay, and the other stuff is just a constant coefficients. And the other stuff outside is just constant coefficients.
This is the q square
Yeah.
plus the mass. This just comes because the divergence. Like we need the integral of this to know divergence.
What is E?
No, this is just a small value epsilon. At the end we just go take epsilon equal to 0. Epsilon goes. This is here because like otherwise the integral will
normalizing.
no for the integral to x.
Okay.
At the end we will take this to 0.
Okay,
Because otherwise like this diverges.
Okay,
This has a
okay.
pole at 0.
Okay, then this makes sense.
You know, composite is at a pole at 0.
Okay. Okay, this makes sense.
Like I'm not teaching it. It doesn't matter. Like, so now you know everything. So you have some propagator terms here. Okay. Propagator is not here. So you have some UV which interact with H with some propagator, H again, UV. So this is what you have. So this diagram is just this. So you just multiply all of them. Multiply all of them. You had a lot of indices. You sum them, integrate them. You get. If you do that, you will get this. You get this thing. This integral plus integration all this. Like here, we had a space integral. We Fourier transform into the momentum. That's how this became the Fourier transform of the momentum and not the propagator. Yeah, I know you. Many of you guys are lost. Like, I'm not saying like the next part coming is disconnected from it. It's not. I mean, it's in a sense disconnected from what is here. Guys, ask doubts, please. I know you guys are lost.
Okay, I'm asking.
Yeah.
Although I didn't understand anything, but tell me, what is propagator?
Propagator tells you how it propagates through space-time. From one point to another, how it goes.
Okay.
The time evolution between those.
Oh, and actually you say propagator and I had made it propagator. That is
Particle physics propagator. Huh?
So like when you evaluate it, like when you remove the epsilon term and you evaluate the integral, it diverges. So like
What this comes from complex analysis. You do this, even mathematicians do this.
okay, then it's good.
Classic. Even though you're not a bad person. So we do that. So we add them. We get the if you do all of this, you get this dirty stuff. This you will get by doing some problems. You will see how to draw the diagram. The terms you will just look at a table. I also don't remember those. I can tell you what are the tables. Anybody who does this book, you can look at the table of what these terms are. You write those. You make computer multiply it. At the beginning you do it, then you make the computer multiply it. Okay, you add those. You get the S matrix. In principle, once you have that, the problem is solved. Now we can do experiments. I don't get.
So what do we do?
So we are out of that.
Like
That-
we make the computer do so.
Yeah.
What
No,
do
we have experiment. We compare them with the experiment.
I know, but if we are given a problem, then why only can we do it? Like if I give it to an AI, will he be able to do it?
At least as of now, AI is successful. At least as of now, AI is successful. In future, obviously, of course.
Wait, so if we are asking the computer to do this, what is
No, we do specification. We do it to do the computation, do the integrals and multiplication. The computation part. Like there are packages in Mathematica you can use these details and it will do them. So these are the end of the Feynman course. Some of you understand, some of you don't understand, some of you get some mild idea.
What is
That's fine.
proper combinatorial factor mean?
Because like if there are, because in some cases like there will be multiple diagrams of the same type except you interchange them.
Okay, and those matches called as.
So those are also like those for those you have to add, like you don't draw the diagram twice again, right? Just add them, you add the combinatorial factor.
Okay. And if you
Before that details like it's very huge details.
if you just like do like that, then why do you have to do like the one by n factorial into a t thing? Why can't you just do into t and into the n factorial? And just
Yeah, in many of the cases they do, but there are some specific cases they do.
okay.
Most of the simple cases they do.
Okay.
Either n factorial or you define the g I to have the n factorial.
So they
You define the gi to have the n factorial.
Yes.
The n factorial comes from the vertices.
Yeah.
So
Yeah. Okay.
and odd is again if you have a function, if you replace interchange two identical fermions, it will create the negative. That's not that. There are some negatives. Now that thing is over. Now we are getting to interesting part. All of the things I had to do because I had to do so that I can say this. But it's not like I go to refer those, okay? Only at the end I'll just mention it. But without knowing such a thing exists, there's no point in going there. This is actually the mathematical interesting part. Mathematics and physics. Other things you learn once, you may commit it. Like I put it in the question, 1 or 2 people did that. If I had done that, I also hate that question. But I don't want to do the computation. In my life, I have only twice done the computation. Everything else I just put in the computers. Being a particle physicist. Yeah. Now, anyone have heard the name of the theorem? Noether's theorem. It's also used in mathematics, in geometry and physics. Indifferently. Instead of here Lagrangian means this will be some geometric function. The Lagrangian itself is used in mathematics. Trust me. Like suppose you want to find some minimum distance, something like this. This. Even if you have, there are JE kids here. Even I think some JE kids would have done mathematical problems with Lagrangian. I used to do it. I mean, this is high school.
Would have done what?
If there are JE. Huh? What? Huh? I can hear you.
Those who just want to like they are called J Nasir.
Okay.
Okay. Now you ask many questions. How electrodynamics works, how chromodynamics works. You ask, right? What are the forces? All comes from something called Noether's theorem and Dyson. So we look at what is Noether's theorem. So, okay, as a simple statement, Noether's theorem says there are symmetries, there are conserved currents, and there are conserved charges. That is language of saying Noether's theorem. If there are symmetries, there are conserved quantities. But
Yeah, there is now consider some transformation except with a function of x, then what is their what is the symbol?
Epsilon
type symbol.
is a small variation.
this epsilon c.
No,
That's called psi.
psi.
This
Now,
that is a Greek letter psi.
psi.
Psi, P-S-I.
Oh,
It's a Greek letter. You haven't seen psi?
no, I see phi.
Yeah, phi is brother of psi.
No, it's
I use psi here only, na? No, I use psi only. You didn't ask that. It's just a Greek letter, okay? We should stop it using English. We should completely switch to Greek. Yeah. So what the Noether theorem says is, suppose a system. The system means it has a Lagrangian and it has a laws of motion. It has an action. That is what a system is.
Epsilon. Any real.
Huh? Actually, can't do it. It's a function. It's not f dash. It's f dash. It's f prime. Fn. It's just L field.
Epsilon is any real number.
Huh?
Epsilon is any real number.
Epsilon is just a number, constant.
Yeah, it's an any constant.
Yeah. Real.
Okay. Yeah. So, in the second thing, what do you mean epsilon depends on x? If you have epsilon as a function of x, then how do you know it's still invariant?
It's not.
I mean, how do you know it still leaves actually invariant?
It's not. That's not.
Oh, okay.
That's the entire point.
Okay.
If it does, then it's a trivial statement. Who cares about it? So, like this, most of, if suppose a theory has such a symmetry, or if you replace all the psi's with psi plus I epsilon times a function. Okay, it's just a function of x. If you do that, suppose a system has such a symmetry, then what does it has symmetry means? It means even if you replace this on the action, you get delta is equal to 0. Which is same as saying this term goes to 0. Okay? Like assuming x, like, okay, here no assumption. Fine.
What is J?
Huh?
What is J?
Let me reach there.
Yeah.
Let me reach there. I am still here. So I have a, this is something called a global symmetry because epsilon is not a function of x. Epsilon is same everywhere. So it is called a global symmetry. Okay. Now I impose. It is, can be considered as a axiom. Not everything. For some cases I consider axiom. Okay. I impose that this is a local symmetry, which means the epsilon can be a function of x.
Okay.
Epsilon that even if the epsilon is the f is not changing. Okay. The f is the same as before. I impose if this is true, then this should be true. I impose that as an impose statement, which has intuitively many reasons to do it. Not like in the sense physical reasons, intuitive reasons, which had before, but now we just take it as we impose it. But then it no longer satisfies delta s. We need this term to be 0. That is what we mean by we need this symmetry. By what we need, by we need the symmetry, we mean we need delta s to be 0. Okay? Which is same as saying we need this to be 0. Because this is the extra term coming from. Like if you put epsilon, there will be derivative of epsilon coming. Initially this vanishes because epsilon is a constant. But this does not vanish down. We need that to vanish down.
What is the J that is J over there?
Which
What
is that?
J over there?
But
What is that J next to that del epsilon by del x?
the J here.
Yeah. That constant of the J.
Oh my god.
D4x J.
Oh, I forgot to mention what J is. For now, say this is like whatever the coefficient is, I call that J. Like that's the definition of J. J is the coefficient of this.
That's the definition of J.
That's the definition of J. It will be when there is a Lagrangian density, it will be of this form. Okay? That's the definition of J. Like delta S has a non-zero term coming from this, which is a coefficient of dou epsilon by dou x. I'm defining that as J. Okay? Understand this is summation, okay? Mu repeated. You sum it. This is very important, okay? Therefore, every slide.
Do they know the summation class?
Yeah,
That repeated.
I told them in the beginning of the class. You also don't listen. I'm going to call you right now. Okay, so we need this to be 0. We impose that. We are imposing the action or the Lagrangian should be such that this is 0. If we impose that, saying this is 0 is same as saying this is 0. You just do integration by parts. This integration you just do integration by parts. Which is same as saying this is 0. Okay? Guys, please ask. Now we are going to, after this,
What is J?
this is the definition of J. This is the coefficient of dou epsilon by dou x.
Why do you say it's also true with arbitrary epsilon x?
Huh?
Why do you say it's also true with arbitrary epsilon x?
I want it to be true for us. I am imposing that.
But how? Isn't it a very strong thing to say?
Yes, it's very strong. Lorentz invariance and the gauge symmetry. This will come to something called gauge symmetry. It is something strong requirement we need for physical.
But epsilon of x is any smooth function or what?
Huh?
Epsilon of x is any smooth
Smooth.
function?
Smooth goes at like decay at the infinity, something like that.
So it's also L squared.
Huh?
It's L squared. It's also in L squared. You said the starting L squared.
Yeah, it will be a square. Is it a square or one square? I'm not sure. It's a smooth enough. Sorry for the mathematics. It's a square, I think it should be a square, but it's improved. I don't think we should. No. Let's say for now it's square. That's what I had said, like that vanish at large space infinity. That is what I meant to do. When you integrate, it vanishes. Guys, where are you guys lost? Like this is just the mathematical foundation for the interesting physics.
We get it.
So, okay, remember this. If we have a global symmetry, if we have a global symmetry, we are imposing it to be a global symmetry. If we do that, we get conserved currents. These are called conserved current because this is zero. The divergence of this is zero. So we call this conserved current. And also we get something called conserved charge, which is the integral of the zeroth component of J. We get this is also constant. For example, in electrodynamics, we increase the charge of electric charge, like the charge.
Like both of them are globally conserved.
Yeah, these are constants of motion. That's why angular momentum is a constant of motion. Like that. Like if you do this rotation, you will get angular momentum is a constant of motion. You literally get that.
What would be the exact rotation?
Sorry.
What would be the exact rotation? You said that you will do this rotation. How would you do it?
Sorry. I think it is expansion. Actually, I think it will be expansion. Accommodate XP minus K. Like I think it will be. Do you remember? Right? Do you remember the F for the for rotations? You had assignment on this. I checked it. I gave you mark. You had to say it.
Okay, for what now? I will pull up the assignment only.
I think it is something like this is angular momentum. No, what's the transformation that gives angular momentum constant for Lagrangian for rotation?
I should know this.
Yeah. I'll point it. I don't feel this.
I forget. Like I need to pull up my notes or something.
Trust me, this will be angular momentum. Sorry about that.
I mean, because if it just get addition, how you get rotation? I mean,
Oh, this is kind of equivalent to doing this.
also this is not. So this is addition is commutative. Very simple.
No, if you see this is something called Lie group. Have you seen Lie group?
Ego. Isn't that just a group which is also
No, this is the structure of the group. Like, okay. For now, I will say, does this looks like for small theta? This looks like e to pi theta.
Okay, for small theta.
Okay, yeah, theta times psi. Does this make sense?
Yes, but that's only for small theta.
Yeah. I'm saying is. Like this is something called the Lie group structure of it.
Okay, so basically saying you take very small epsilon and you like.
Yeah, for now.
And you make it like you exponentiate it, like you take smaller and smaller generating.
So you can say this is a if you consider a differential equation, it transfer corresponds to the.
So
Like think of it as a differential equation. Then it corresponds to the exponential.
Okay, so is it actually just like so just saying you are taking smaller and smaller generating, like generators? What are
Yeah, this is the generator. This is the generator.
So you're just taking small and small generators.
Yeah. Usually, what you call the generator is the first order
Okay, that makes
for the Lie groups.
Okay.
Lie group or Lie groups. No. The infinitesimal generator for the Lie group. That's what it is. We'll come to all the angles theory, everything is coming from that. So what do we have? Can you guys say? What is Noether's theorem in language?
If we impose symmetry, then they are conserved.
What symmetry? If you impose a local symmetry to be global symmetry to be local,
Then they would be locally conserved.
globally conserved. These are globally conserved. In the sense, it's conserved. I would say globally local. It's conserved.
Like if it's
Conserved current and charge.
Like if it's locally conserved, it would be globally conserved.
Like the terms here is like for different reasons. Usually, if you say global local has different meaning, like classical. This is something different.
Why would comma between them? Are they equal? Del u equal to 0 and del q by del p equal to 0.
What? No, these are not equal.
Then Like for u is equal to 0. Oh, you're doing summation. I forgot. That's weird. Okay, yeah, that makes sense.
Huh?
Nothing like it, remaining sentence.
So can you go back one page? Yeah. J, why J is 0 just?
Huh?
Why just J is 0?
Where is J? J is the 0th element of J.
Why does it not go for J1?
That is no. We are taking a time derivative.
So J0 is just the time.
Yeah, time common.
Okay.
So we are taking time derivative.
Okay.
By what a constant of motion we the time derivative is 0. But we give a constant of motion.
Okay. That makes sense.
So what were you like your standard was like 10 standard or where is the 10 standard? You guys understood the question.
What is the standard? Class,
Yeah.
standard.
Yeah, class 10.
Grade.
Class,
Oh, sorry. Like I can understand 10 people cannot understand. Even plus 2 people this will be very hard. Sorry for that, okay? I understand it. When I prepared, I understood it is very hard for testing. Even for now we will see by just this road, by just imposing these things, we will see that electrodynamics gets bored, chromodynamics get bored, electro V theory gets bored, particles get mass. We will see this coming, okay? It's not words, this actually happens. Okay? So again, I'm saying this again and again with that important. When you have global symmetry, we impose them to be local symmetry. Then we have conserved charges and conserved currents and constant motion. Fine? Say it together.
Fine.
Not fine, that's the other theorem.
It is that if you have a symmetry, continuous.
Global symmetry.
Continuous.
I mean, smooth.
Smooth continuous symmetry, which is like just generated by one field. Generated by one field, and it's a symmetry that doesn't change action. And then you say ki R is also true for local stuff. Then you can say ki there are certain things are conserved. In particular, the coefficients of it, of the delta S, when you make it local, the coefficients of the delta S, that with respect to the if it's space coefficient, you take del by del x.
Divergence of it is.
Yeah, exactly.
Okay,
Yeah.
good. So, now for doing this, for imposing the local symmetry to exist, what I use the word is, I promote it to a local symmetry. If you guys had the UG paper, you will see the word promote to local symmetry. Maybe see the promote. Even though I put the paper. Now we are getting into electrodynamics. We had some abstract equations here. Now we will see how electrodynamics works. Now consider a global symmetry of this form, okay, which does exist for the so if you look at the equation of motions of the free field, you will see that such a global symmetry exists.
What is U dash?
That is what QL. The letter L.
What's UL?
Q corresponding to psi. Psi L. Psi, remember L is which particle it is, which representation it is. Huh?
Q.
Q.
What is the Q?
Different. Just Q. We will come to which after.
Okay, it's just for some arbitrary
It's
constant.
it's constant. Like I'm just taking the constant out of it. I'm defining FL to be Q psi. Okay? Yeah, so I consider variations of this form. Now we are doing the same thing we did in this slide. We want to promote this into a global symmetry, local symmetry.
I would like to ask you how.
Like there is right.
Yes.
What's the
point?
Well, this is the last lecture, right?
Yes.
There are no calculators, but still we have to ask.
Please. Yeah, like after this I'll go fast. Like once we are comfortable with one theory, I'll go fast. After this, just take them. So now this is a local symmetry. we made it a local symmetry. So now we take the derivative, variation of the derivative. We will get a, this term already was there. Okay? But this term is something new. But we don't need this term. This term will break the Lagrangian action. This is the term that makes the action not, the delta of action is not zero.
Yes.
So we want to cancel this term.
Right.
To cancel this term, we will define a new field.
What?
A new field,
Okay.
particle.
Yes.
A new particle, a new field,
Yeah.
which is a new.
Yeah.
It's a vector field. Like it transforms as a vector. The field can be scalar. In the sense it has 4 components.
Okay. Okay.
Can have infinite components.
Sure.
The representation has 4 components. It's a specific irreducible representation of the law. It has 4 components, transforms like 4 vectors, and satisfies something called Roche equation.
This capital T is the covariance.
It's something like this. Yeah, covariance.
Okay.
You know general relativity. We didn't get to that. Hey, you know general relativity. How did you not understand all this?
I did not understand it.
Huh?
Why did I say do not understand?
Okay, fine. Guys, so we have how many people understanding it? You understand? You understand? 1, 2, 3, 4. You understand?
Yeah, understood.
Ah, you understood? Good. It's going good.
पूरा presentation दिख गया.
Guys, be aware, the moment you understand, you may receive a quiz from the morning.
Yes.
I did this. What is this? This one.
Sorry. Let's continue.
Okay.
So for cancelling this, we need the existence of a new field, which has a vector property in this case, because like it's a term like it's a field such that this is true. Okay, the variation of a mu, like a mu transforms to a mu plus this. That is what this means. Like whenever delta of a field, that means the term that was here. That is what I mean. So here that term is dou mu of x. Now this will, like, this is just multiplying, this will cancel this. Okay. So okay, there is a lot of way to choose this. Like this is not uniquely determined. I will make it unique by imposing that the spatial divergence of this is 0. I just impose this kind choosing a gauge. Because we need to fix an A, we do it by fixing this gauge. If you are done general relativity, you will see the same thing when you go to gravitational force. Like it happens in electrodynamics, or like in gravity comes in Christopher's universe. Good. Now we need the Lagrangian. Like how we will impose that the Lagrangian is invariant under the transformation that delta goes like this, A goes like this. Okay, this is a combined. Okay, you don't just do this. Whenever you do this, you do this also. Okay. Now for to make sure that our new Lagrangian is invariant, we need the Lagrangian to be a function of the fields and something called the covariant derivative of the field, which is defined to be this. This is called the covariant derivative.
Why?
General relativity. Also, this is covariant because this is the lower index. Do you have a lower index? You call it covariant. Not just that, it transforms covariantly. Like there is 2 types of, there is invariant, just stays the same. Covariant is it transforms as we want according to how other changes. It changes, but it changes in a way we like the equation solution. Heuristic. The name comes from general relativity.
Why are you doing minus I2 dash?
No, this is what ensures that Lagrangian.
Okay.
Like you like the Lagrangian of this, you will see that this satisfies the Lagrangian. Okay. So what will you do if we have such a symmetry? QD is this. If we do this, we get QD. Okay, this A mu is a photon. The A mu, the field we said should exist is a photon space.
Okay.
So this is the like you can say charges. If particle with charges exist, the photon exists.
Okay.
But this seems good, right?
That seems nice.
This is how everything exists.
That's nice.
This is how mass exists.
How does mass come from here?
That's a goddamn particle story, right? So all the same thing. Like everything is same. Everything is using gauge symmetry and Noether theorem.
Okay, nice.
Like gauge transformation correspond to this specifically. you multiply with the sign instead of any arbitrary f.
Yeah.
So you do this. Now you have photons. We need a photon for the theory to exist, to be invariant. And we also need to replace all the dou mu by the d mu. This is a covariant derivative. We replace all the derivatives with the covariant derivatives.
So is this why photons travel actually outside because they are invariant?
No, because when you put off this, you will not get any mass. Like this Lagrangian, when you, like if you are introducing a new field, you need a Lagrangian corresponding to the photon, right? Gamma means photon. If you are introducing a new field, you need free equations of that also.
Yeah.
That also has a life. They don't exist therefore interaction. They also have a personal life. So they have some form, which we will see will be spoilers. Okay, something of this form. So when you add this, when you have this with the already, we already have a matter Lagrangian, which may come from Dirac equation, Chromodynamics equation, some equations from Marshall, which defines the representation, which defines the representation that fields are solutions of those equations.
The first term is just the classical became, right?
What? First, which first term?
Minus 1 by 4.
Yeah, that's right. That's a very speciality of Maxwell equation. You take relativity, you take quantum mechanics, Maxwell equation stays very strong. This money generally by no change. This is Maxwell equation. If you apply Euler Lagrangian to this, you will get the Maxwell equation. That is nice. Why do you think I'm interested in this subject? This is very But I'm most okay. If you ask or consider every field, what my favorite thing about any field is gauge symmetry. It was before it was special relativity, but when I studied gauge symmetry, it became yeah. So we define something like this, something called covariant derivative. Now, you ask why does it not have mass? The Higgs reasoning will come. But here, if you write this with a mass term implies m square a something like this. If something like this exists, then it is no longer invariant under the gauge or the norm.
So why can't we
The
second?
norm it is gauge.
Oh.
If we have a term, if you have a mass term like this, then it is no longer gauge invariant.
Okay.
For it to be gauge invariant, we need the mass term to be 0.
Okay.
Which says the mass of this field is 0, and we, by experience, we identify this from our experience. Yeah, so we got a covariant derivative. So I will. This is QD. Okay. So we had what? We had a. This is something called a U1. Like I said, this is a Lie group structure. Correspond to a U1 Lie group. The set of unitary matrices. One by one unitary matrices, which is same as numbers of e to the power I theta, where theta is 1. Because the determinant is the norm is 1.
Yeah.
Now the determinant, the norm is 1. And you take the summation, it becomes minus. You know what a unitary matrix is, right? Unitary matrix. So U is called a unitary matrix if U finite dimension. Dagger. Where dagger is the transpose of the complex quantity. Okay. So if this is equal, then we say U is unitary. So this what we will say is a U1 Lie group. Huh? Oh, what am I saying? Sorry. Sorry, my bad. Yeah, I have QM codes. That's why. Yeah, so this is called if the I satisfies. If a matrix satisfies this equation, we call it as unitary. So this is something called a U1. Okay, now we will look at general UN after QD. General UN is what Young's theory is. This is a special case of that. This came in early 1990s. People like Feynman. Yeah, so what did we do? We need a gauge symmetry. We had a global gauge symmetry. We promoted to local gauge symmetry. Okay? By how? For that we need a new field, which we will call photon field. And with we have to replace the derivatives with a covariant derivative. And the Lagrangian has mass 0. Like this field has mass 0 in the Lagrangian.
Where does the new derivatives coming from?
Where is that?
What new derivatives are you talking about in this?
Like this variation corresponds to unit because this corresponds to, I told you now, this corresponds to this variation. This is unit. That's what it means. It's a Lie group structure of the U1 Lie.
Okay, that makes sense.
Like, of course, I cannot use Lie groups here. Then this is going to be always. So, and I also defined something called the field tensor. If you have the classical electrodynamics, you might know about this term. This is called the field tensor. Because an actual equation you can write in terms of these equations, these tensors. So I define this is the definition of field tensor. Just it's an anti-symmetric tensor. Tensor, oh, you guys know tensor?
Which transforms like it.
I'm the same student, okay. When I came to here, I told that, but no.
It is something which is a linear form. It's maps dual vectors and vectors to a field, to its base field.
It's a, for example, a.
Not this field, the other field, the maps wala field.
No, I'm saying this field. Oh, that field. Oh, sorry, yeah, that field. Sorry. Like, you guys know what? You guys are. When we are here, kids, right? You know what a dual vector is? And I know you guys know. I'm asking the high school. Dual vectors. So, like, suppose I have a vector here. Okay? You know what a vector? Vector space structure. Yeah. I define what something a dual of it. A dual of it is a function. It is a function from the vector space. From the vector space to the field. It takes a vector, it gives a, let's say, complex value of real value. Okay. So suppose this is a vector. This will be called the co-vector of it, or the dual vector of it, by just lowering it. So this is just product and sum of some vectors and pointers. A tensor is say arbitrary product and sum of vectors and dual vectors. This is called something called affine tensor. We want to search about it. Yeah. Now we will see how this gives the Feynman rules. We had a Feynman rules. So the simplest Lagrangian, simplest means there are no higher terms. The higher terms has a problem in renormalization. You told why the converging problem now. If we consider something complicated than this, then it will be no longer convergent. That's what it is. So this is the simplest consistent Lagrangian in terms of the field tensor.
What do you mean?
Simplest means no divergences. Like you can have maybe there are only quadratic. There is no higher derivative terms or higher terms. Okay. Because this adding to the other one leaves it in. Okay. Now the equations of motion will be the charges is this. Okay. And okay, this part when I say something like this means you sum over the cyclic combinations. Like dou 1 f2 3 plus dou 2 f3 1, you sum those three. Okay.
And you don't minus the anti-cyclic.
Yes. This is what I mean by that. So from this Lagrangian, we use the Lagrange equation. We will get this equation, which is the Maxwell equation. This equation, these two are combined, known as Maxwell equations. Okay, which is beautiful. We assumed a U1 gauge symmetry. We promoted it to. We have a U1 global symmetry. Indeed, we have a UN global.
I'm confused on what I'm confused about. But I know I'm confused about something.
Okay, so I will. So we are done with QA. Okay, now we are just analyzing all the terms.
Yeah, sure.
QED is just the first course up to that, which I call QED, which call the rest of this thing. So we had a local global UN symmetry.
Yes.
We promoted to global symmetry.
Yes.
We have to introduce a new field for that,
Yes.
which we will identify as photon and it's massless.
Yes.
It does not have a charge also.
Yes.
It comes from like Lagrange.
Yes.
I'll come to it. And now this we define something like covariant. Also we had a covariant derivative. This much leaves the
Is it because of covariant derivative? Is there something like a contravariant derivative?
covariant doesn't come from the contravariant covariant. It comes from the word covariant, not from covariant text. Like something that transforms covariantly. Which is your covariant. So this is the Lagrangian we have for that. This is only the only part of Lagrange. Okay. Therefore, just for now, suppose we consider a simple case of a particle, a spinor particle. Spinor means the spin half particles we know, electron, proton, quarks. These comes under the representation called the spinor particle, which is the wave function of which will look like a column matrix with 4 entries and satisfy something called the Dirac equation. Okay. It has 4 components. That's important. Now, for electrons, like all the spin half particles are spinors. Their wave function look like spinors. So we consider spinor of charge minus e, which corresponds to electron, muon, tau. They have minus e and spin half. They are spinors. And the quarks, the only difference is e minus e become e. Yes, unless it is QED, not that is QED. Now the Lagrangian, again simplest Lagrangian without hierarchy, is this. Now this may look messy for you. That is actually good.
Yeah, it looks very small for what you are doing.
Yeah, exactly. We assume something strong but simple.
Yeah.
We are getting the entire QED, which humans are here for lakhs of years.
No, crore.
Lakh.
No,
2 lakh?
No, it's
Not crore, that I'm sure, not crore. Maybe it's million, not crore.
Yeah, we need one.
Okay,
100 crore years. That's
100,000, not crore. 100,000 is
100,000 lakh.
lakh. And we are doing farming from 14,000 years. And this is coming from last 2 centuries, 1 century. Okay, last 1 century, okay, electrodynamics come before, but it was just magic for us. But now we have a mathematical understanding. So this corresponds to the how the electron evolved, not electron, photon evolved. This F mu nu part says how the photon evolved.
Yes.
Now this is the spinor. Psi is a spinor. Psi has 4 components. Okay, psi bar is something. I'll come to psi also. So, we'll first explain the terms. So, spinors are coming from a mathematical algebra. It's called the Clifford algebra. It's a name of person. It's an algebra satisfying. It's an algebra satisfying this equation. This is the definition of Clifford algebra.
What's gamma?
Gamma is something that satisfies this. Matrices here, for our purpose, matrices.
Okay. So Clifford algebra is just 4x4 matrices.
4x4 is a particular representation of that algebra.
Okay. What's the general Clifford algebra?
There are many dimensions. Physics are only concerned with the 4x4.
Okay.
Now, it's an anti-commutator. So this is where the anti-commutator is coming. Spinors are fermions.
Yeah.
So they have anti-commutators.
Yeah.
Okay.
And U is like the.
Eta mu nu is a diagonal matrix. Is something called metric or the Minkowski metric. This is -1, 1, 1, 1. -1 in time, 1 in space, and so on. That's what it's a elements. And I is just the identity matrix because the metric is equation. People sometimes don't write this, but now one representation which you can use is this. Many book have many references. I am using Weinberg's. No, Weinberg like what that big. This is gamma naught. Gamma I correspond to 1, 2, 3. Whenever I use I, 1, 2, 3, which is Latin, Greek, mu, 0, 1, 4, 0, 1, 2, 3, 4. So this is something as polymatrices you might have heard about. Like these are just 3 matrices, like standard matrices, something like looking like they are the polymatrices. You Google, you will get the polymatrices. You haven't heard polymatrices.
I've heard that, like, for what?
Yeah, there are some matrices, 2 by 2 matrices.
Okay, they're specific matrices.
Yeah, specific 2 by 2 matrices.
Okay.
Like matrices like this one, like one is like this, one has like something like I also don't remember. Okay, so this is one way to write those gamma matrices. If you use this, you do computation, you will see this satisfy that.
Yeah.
That's it. This is representation just means this satisfy that. That's it. Now the spinners satisfy. Now I write spinners. You remember when I had a field, I write it in particle antiparticle terms. U, V. The U satisfies this equation.
Yes.
V satisfies that equation.
Yes.
Where when I have a vector V, I define V slash to be V mu gamma. That's the definition. Okay, when I write it is a matrix, okay? Slash is a matrix because these are matrices. So this is my definition. So linear combination of the gamma matrices corresponding to the component of vector. When you see slash, it is this, okay? I think I have written that. I don't have. So this is that. For the U and V part satisfy Dirac equation. These are the Dirac equation. This is the Dirac equation for particle and antiparticle. Okay. Now that's it. Now we look at this. So now we understand all the terms here. Do you guys have any doubts? Trying to clear the doubts. Any doubts in this equation? So now like
Why would we do spiders? Like, why spiders?
electrons are spinors.
But why?
Nature is like that. Nature is like that.
Yeah.
Nature is like that.
No, why would you do the? Why would they have that Clifford algebra?
It's a representation of Lorentz.
Okay.
The Clifford algebra is a representation of Lorentz.
Okay. Okay.
Like this is I am saying many heuristic algorithms. The derivation of the field and field equations come from same representation. Okay. Which is actually the hardest part of studying QFT. Once you are after, that's not your first study. If you are studying in mathematical rigor, once you are after that, then you rust is like you it's like you start by climbing a mountain, then you just land flat. It's like that. You have to first come through the hard part. So actually, one thing I have to mention is I am going here very fast. Not going details, no derivations, anything. There is something called QBit. So it's CMI undergrad physics initiative team. It started this year by the physics students here. Arjun, Arshira, Ryan. These physics people use only that. We started that. They are conducting seminars. We upload them to YouTube. 2 seminars are already there. So I am doing a complete seminar series on QFT particle physics. So I cover all of this in great detail. Okay. So like, this is I am giving an idea. If you want a proper idea, you can see that. I can refer it. And we will be creating a Discord group or something where you guys can ask doubts. We will give interesting problems, books, stuff. Just advertisement. So if you look at that, if you calculate J mu, we get this. And if you substitute this equation, like the spinner values here, you will see that this corresponds to the currents we are familiar in classical electronics. The electric currents, current densities actually. You have seen the current density. The zeroth component is charge density. That corresponds to different derivatives. This corresponds to the what we see in classical mechanics. And yeah, like the conserved thing is the same as the charge that we took in the beginning for the gauge symmetry.
Yes.
Now, yeah, so this is the definition of psi bar. So it is a Hermitian matrix times a So this is called psi 1. So it is the psi Hermitian times this matrix I gamma 0, or what I call beta. Okay.
Okay, what is P slash?
I told you. Yeah, so now we understand that we have a Lagrangian, but what is it? We need final rules. We need what the vertices to take, right? Like we know what are the UVs which come from folding the, like you can look at the any book. Stop from folding the Dirac equation. You will get that. They have some forms. That is fine. What are we interested in? The vertices, what the vertices look like, which explains the theorem. So what is the vertices look like? So here, without this term, this is just the Dirac equation. Without the A mu, putting the E equal to 0, this is just the Dirac equation, which already we know how they did. And this is just the how the photon propagates. Those two things we are like this corresponds to what the photon goes like. Those two things we are not interested in. What is the extra term came down? Because we replace the derivative with the covariant derivative. We got a term. I E A mu. Gamma mu. So we got a interaction term. So look at this. What is this? This is a spinner interacting with the photon and a spinner body. Anti-spinner. Anti-spinner. Anti-corresponding anti-particle. These are the same psi, okay? If this is an electron, this is the positron. Okay. Now we will see that this is the interaction term. So we remove these three things which are the fields. We get the Hamiltonian, which is I E gamma. So we get we had a GI, the GI, right?
GI. Right.
Which is the coefficient of the monomial.
Yeah, the complete thing.
No. GI is very, it have a component, but defined to be this.
Yeah.
Coefficient of the monomial.
Yeah.
Hamiltonian monomial. Yeah, so we are done with QED. So this is the vertex we get. Electron comes. Okay, we can look at the differences. We can rotate it. If you rotate it, it is still meaningful. That's a property of Feynman diagram. If you rotate it, it still is meaningful. So this, suppose we are taking time up. We will look at it as electron coming, a positron coming, narrowing for positron. So it's antiparticle. So electron and a positron coming, then annihilate. It become a photon. You say particles and antiparticles annihilate each other. This is what happens.
There should be two photons, right? There should be two photons, right?
Oh, yes, I agree. You are saying this does not correspond to a, like, if you just consider this Feynman diagram and do the integral, you will get 0. You will only like, but what you are talking about is something like its first time is 1.
Yes.
Okay, like this has non-zero value of S matrix contribution.
Why is there 0?
It's mathematically computatively.
It is a big nice symmetry for why it's 0.
No, there's a momenta cannot be considered here.
Yeah, oh yeah.
I think you have heard it.
Yeah.
Like in here, momenta cannot be considered.
Yes.
It's just normal algebra. Okay, so we get this vertex. We can think about it in many ways. One, electron positron coming, annihilating, or electron coming, photon hits it, electron going out. Electron comes.
Yeah.
You can think about it. Or it comes, it emits a photon, goes as an electron.
Yeah.
Electron comes, emits a photon, goes. Anyway, you can look at this. Same with positron. So we get the basic vertex. That is QED. So we by just assuming by just promoting a global gauge symmetry to local gauge symmetry and imposing that, like, by doing that we got the entire mechanics. The only experimental part is getting the factors like E, and the masses of these, the masses of the electron. Beautiful.
I suppose I cannot say it will be.
Huh?
You can
The QED is done. Now we'll go to animal theory. The channel. This is for U1. I'll go to UN. Now this is looks more dirty because I didn't go enough time to type. I didn't type in nice type. Yeah. So what dynamics theory says is, so who are the UG high school physics test people? U3, yeah. U3, U2. No, you are not. Yeah, fine. So there was a dynamics theory question. Quantum dynamics. There was a quantum dynamics question in the question paper for undergrad physics. We are going to solve it. Okay? We are going to solve it. I am not going to give every step. This is for, I am first going to state it for n dimension. Then you look at the special cases. Now you consider a spinner, you consider n fields, n spinner fields, which are distinguishable but have same mass. For example, red up core, blue up core, green up core. So in different fields with the same mass, spinner fields. We write them as a column matrix. Now the free Lagrangian look like this, right? Dirac equation. The free Lagrangian and the Dirac equation. Here if you look at this, you will see if you multiply by a unitary matrix which does not depend on space, this takes the proof, because if you multiply a u direct here, u here, this bit that cancels and become 1. Okay, so this has a, guys, you can say so this, if you look at this has a global. Okay, so here I have a mass equal term. That's why I have this term like this. So I have a global UN symmetry. A n by n unitary matrix is a symmetry of a global symmetry of this equation. Okay. Now I need this to be a local symmetry. I promote the global UN symmetry to local symmetry, local UN symmetry. Just by putting the epsilon, like it's not a simple epsilon here. There are n epsilons here. Not n epsilons. Sorry. It's not n epsilon, but like it depends upon the representation of the group here. Like the number of alpha is depends upon the water or E group is. Okay, like for example for SU3 it will be 9. Okay, so it depends upon the representation. Now we promote this. Now something in group theory is that the UN group can be decomposed into U1 tensor product or direct product, whatever, the SUN. Okay, this U1 gave us what? U1 gave us what? Studying the U1 gauge symmetry gave us QED. Studying the U1 symmetry gave us QED. Now we will focus on SUN symmetry, which gives us the other forces are there. Because all of these particles, all of the particles, spinors have charges. That's why this is always there. Yeah, so okay, now I'm going to do some abstract math, then I will come to the special case of QC. Not abstract in that, that's it. Like these, they have, like the variation will be of this form, where the T's are called, T alphas are called the infinitesimal generators of the loop. They satisfy something called the Lie algebra, we call this structure constants. They are real. For example, in 3 by 3 this will be just cross product. Like this will be the T corresponds as a cross product. Because this will be like epsilon I, they will see it as a. Now, we need what? Lagrange we need. For that, what do we need? We need a new field. Now there are some, let's say 9 fields. What are alpha goes to? Some new number of fields. According to how many alphas are there. A new field which transforms like that. Okay? And we have a new covariant vector. Similar, same thing. And for F matrix, the F is related to the commutator of D. Okay, so that's why F has a different form, because these C's are not zero. In U1 these C's are 0 because it's a abelian group. This is non-abelian gauge theory. So these are non-zero. So these terms are important. So we have the usual partial derivatives of A and an extra A square with coefficient term. Agree? Fine?
Okay, I am confused. Just read this again. One.
Any other doubts? Question? Any doubt? If you know what are strong forces, this is how what are strong forces. Or nuclear forces. Nuclear forces, these are nuclear forces. No, like, don't talk about it. This is Lie, don't talk, think about Lie algebra.
What do you mean real structure constants?
These are called structure constants. These are the names for them. The coefficient of the commutator is called the structure coefficient.
Ah, it's just called that.
Yeah, we call that. It's called structure constant of the E.
And what is TB?
They are the generators, the principal generators.
Okay.
Like we had similar to the
Okay. What U of n is not the
yeah, you should not commutator.
Yeah, the rotation.
It's not abelian.
Yeah. So what is the, can you tell explicitly what is the symmetry, what is the abelian, what's the commutator subgroup of SO, S of UN? Like what's the commutator subgroup of U?
You're saying what's a normal sum? UN.
Yeah, what's the commutator subgroup?
Normal subgroup.
Yeah.
A median is just which.
I don't know. Such
I
a
don't know what it is. Like, I don't.
I think it is U1 only. I'm not sure. I'm saying I don't know. Just a bit answer. It may be hopefully U1.
If it is UN,
Oh, it's not a subgroup. No, forget it.
if it's UN, then it's trivial.
No, it's not U1.
No.
So I don't know. Answer I don't know. Sorry for that. You can search what is the normal subgroup of U for UN. You can search that and I don't. Like I have searched it when I studied it.
But it exists. It's not something.
Yeah, it's found it.
I mean, obviously.
I mean, at least trivial. At least a trivial.
What are the language?
So what are these? Oh, these are the STEM t-shirt. I did. Can you show me the back side?
Not the best.
I don't know.
Why is that field tensor looking a bit weird, the last field?
Yeah, because the field tensor related to the commutator of D.
Yeah.
This looked better because this C was 0 in the U1.
Yeah.
Because it's abelian.
Yeah.
Now this is the non-abelian coefficient.
Yeah, this is
Median is which.
Abelian is commutator.
Yeah, this makes sense. This makes sense. It
Makes sense.
Makes sense.
So we got what? We did a self stuff. Whenever we do QD, here we just have more number of T's. Yeah. So with the Lagrangian beauty of this form, we'll have this same term.
Yeah. What's LM?
LM is the other matter.
Oh.
We have the usual one,
Yeah.
except we replace the partial derivative by the covariant derivative.
And it can be any weird function.
No, we already had. For example, here like this.
It's the same only.
Yeah, same one.
Okay.
Except the partial it will be covariant derivative.
Okay.
This partial will be replaced by covariant.
Okay.
That's it. That's it. Okay. Now, like these are the equations of motion. There are many currents corresponding to some color combination. You said there are color combinations, right?
Yeah.
So there are a lot of conserved charges.
Right.
So if you have 3 and 3 charges, okay, color charges, how many are there? 3 cos 3, 9. Due to a trace property, there are only 8. One is godlike. It requires some argument.
If there are 8 molecules, then why do we have 8 particles in the standard model? Like we have less particles than 8.
No. Gluons come in 8 flavors. 8 colors. There are red, anti blue, anti red, green. Like there are many combinations. Those correspond to the representation of those groups.
Okay, so it was not just one thing. I saw one blue one and I thought 8. Okay, so like 8 blue ones.
Yes. They are actually combinations, not combinations.
Okay.
8 gluons as an anion is kind of photon. Here, because, but we are only concerned the 8 of 1, we already quotient.
So what did you mean then when you said that there are 3 colors total with white hues and the key? Why does it act neutral? Why does it
So
act
that is
neutral?
something from here. But that actually is kind of encoded in here, but you need more work. So there is something called asymptotic filter.
Why do you remove the 1 from the 9? Why do you remove 9 say 1?
What?
Why do you remove 9 say 1?
Oh, because I removed a U1 here. Because U1 is just electrodynamics.
Ah, okay. Yeah, that was easy.
But don't interpret this as a unified theory of chromodynamics and electrodynamics. It is not.
Why is it not?
Like, in the sense, you can add both of them, but it is not like a, for example, equal to something called electroweak theory. Okay, it is not something that fundamental. Like, because we don't have a strong unified theory.
Yeah, but why is it not? Theory, what's the issue?
Actually, don't have that. I think it's because I think
Is it something to do with convergence being difficult to?
no, nothing with that. It's coming with, I think it's coming with mixing it with the electronic theory. I'm not sure about that.
It's coming in one key.
When mixing it with the electronic theory.
And electronic theory is very
I come with. That's the end topic. You already would do all this. You guys are interested? If you guys are not interested, I will talk about the Young's theory, otherwise they can go to Higgs mechanics. And the Gautham V. It's only short.
I'm a bit hungry, so how much time will it take?
Oh, this will take 10. This is QC.
Yeah.
We just analyze part of the budget.
Yeah.
So remember, this is the important part of QC.
Yeah.
Something that QED does not have.
Yeah.
Now, in QCD it is n is equal to 3. It corresponds to the 3 colors. We have every corn flavor has 3 colors. Red, green, blue. That's nothing to do with color. For example, I call it taste in college media. Something which is named. Okay. It's actually called color charge. Then we will say something called hyper charge. So okay, actually I have to make a statement. The Young's theory actually they proposed it for 2 dimensions. But it was for neutron and proton. In the last seminar, the first seminar, today the first seminar, you saw a proton like isospin.
Yeah.
This was usually applied for that instead of color. Because we didn't know about color then. So it was initially proposed for isospin. Then when we got idea of quarks, we applied it for colors and we got the correct answer. Great. So Young passed away last year. Everything I am saying, they have got a Nobel Prize. Okay, which slide got Yeah, so now if you get n is equal to 3, this is be for chromodynamics. This corresponds to something called the Gell-Mann matrices, which is a 8-dimensional representation of the SU3.
Yes.
SU3. It's called Gell-Mann matrices. It's 3 by 3 matrix.
SU1 में मतलब
SU3.
SU3 में
SU3.
don't you have SU in 9 dimensions? I mean, don't you accept the limit not equal to? Oh, that is something else.
The most fundamental is 3, which is the correspond to the color.
You accept limit not equal to 0.
Huh?
So SU3 is the set of matrices.
Which has unit determinant and are 3 by 3 unit.
Unit determinant, right?
Otherwise it's U3.
Yeah.
Otherwise it's U3.
Okay.
This is subgroup of that.
Okay, yeah. So this is SU3. U3 is what?
U3 is the set group of unitary 3 by 3 matrices.
Oh, unitary. No,
SU3 is determinant 1. Whenever you see S, it is determinant 1. Special. Like you can look at, if you want to try, you can look at the Google one is claim.
Yeah.
You get 3 by 3 rows of Now there are 8 gauge fields that A mu is, one of the A mu is like 4. There are other 8, which are the 8 photons, 8 gluons. Okay, there are 8 gluons, which are a combination of charges. Actually, linear combination of charges. They don't exist as just blue green, they exist like half place, 1 by root 2 V plus. That is a property of the representation.
Yeah.
That's coming from literally the T alpha. You
Yeah.
multiply T alpha, you get those.
Okay, that makes sense.
Now, here we look at the. So we had just this. This is our theory, right?
Yeah.
So what does this have? We had psi.
Yeah.
So we have in QED what did we have? That tend to this term.
Yeah.
Here there was just more summation. That's it. No difference.
Yes.
So that gives a usual something just like QED. Okay, that just look like this. Instead here blue. This is not electron. See, something has, these are quarks.
Yeah.
Because electron doesn't have color. Now, photon doesn't have charge. Agree? Gluons have colors.
Because I'm not abelian.
Yes.
That makes sense.
The non-abelian nature, these constants in the F mu nu give the colors.
Of the gluons.
That's why there are 8 of them.
That makes sense.
It's a big thing. Okay?
Yeah, it
These
makes
are coming like last 50 years.
That makes sense.
We reached in last 50 years. We started with Lagrangians, we started in the last 50 years.
That's nice.
Yeah, so what I was saying? So we have that. So we have the usual vertex. Quark changes color, emits gluon.
That makes sense.
Quark gum, take gluon,
Yeah.
becomes color change and goes as quark.
Okay. Makes sense.
Annihilate into quarks.
Yeah, makes sense.
These kind of diagrams we did. So we already had in QED.
Right.
Except we have
Yeah.
more number of charge because of the color.
Yeah. That makes sense.
Here we have more.
We have more.
Because if you look at the F mu,
Yeah.
this product, initially it had only quadratic product. Quadratic product doesn't give vertices. So vertices we need at least 3 points. Right?
Right.
We need at least 3 points. We didn't have that in QED. But here we have a quadratic term here, which on multiplication with this itself give cubic terms
Yeah.
and
What?
quartic terms.
What?
For
Yeah.
cubic terms.
And what?
So the cubic term corresponds to, okay, that is only for gluons, okay. So that corresponds to,
Three gluons galactic.
we don't have in QED,
Yeah, we know.
we have these two. It's a property of which comes from the non-abelian gauge nature.
Okay. So if for some reason we somehow had a field which did not even have quadratic terms, then its 4 particles could not move at all. If for some weird reason we had a
Like, okay, singleton will not exist.
Yeah. So that's what I'm saying. It does not exist. It would not exist.
The field does not exist. It means that is not in the Lagrangian.
It does not exist.
So we don't care about it.
It does not exist practically.
I mean, it's like you have heard about sterile neutrinos.
Huh?
Like there may be particles which do not interact with anything.
Yeah, exactly.
So we don't know about it.
Yeah.
That's it.
Yeah. Makes sense.
Like they don't, they even don't even have mass.
Right.
Suppose there is a massless something that does not interact anyway. Like it's philosophy to say if they exist or not.
Yes. Makes sense. Yeah.
Okay, it's like you can believe it exists. Who cares?
Okay.
So that's the specialty field. So this was the main part of the lecture I designed.
Yeah.
Now just look at the peak into electronic field. Okay.
One question. Why is it called gamma 5 and not gamma 4?
Gamma 4 was ever. Ask me, right? You don't know.
4 was like 50, but
What's the definition of 4?
there is no 4.
No, 4, I don't know. Maybe some historical reasons. I define gamma 5 as this. Oh, no, I think no, there are more independent matrices, right? I think maybe some of them were called gamma 4. No, like maybe in beginning. Then we just drop it. Maybe something like that. I don't know.
What do you mean left and right handed part of the equation?
Huh?
What do you mean left part, right part, right-handed part?
Can't get it.
What do you mean left-handed part, right-handed part?
That's the definition.
That's the definition.
Yeah. It comes from experiment.
Okay.
You have heard about CP, hierarchy violation.
No.
CPT is not violated. Hierarchy violation. Like
I have heard of it. Yes. This was
the weak force has a property that only react with a part of the wave.
Yes. I heard.
It's a property of it. We experiment to observe it.
That's weird.
So we define those as just this. Okay, here E represent the field E. This is it. Okay. And neutrinos, as of now, we only know about neutrinos which are left-handed. We don't know about right-handed neutrinos. They might exist. We call them sterile neutrinos. They might exist. We don't know because their only interaction will be then gravity. Because they don't have charge, they don't have color, they don't interact easily or theta. They may have mass. I mean, they have mass.
They have.
Yeah, but it's very negligible. We can take the mass almost in calculations. Like they have mass due to some other reason. We don't dictate mass to them, but we see some other people, even also Newton oscillations. But you know Newton oscillations. So Newton has something like they oscillate their ideal state, like they change in between ideal states as they move freely, which can only possibly they have mass.
Why are not possible to have mass? So how do you know that they are changing ideal states?
Yeah, because we saw. In the beginning, we sent, let's say we sent all of many electron neutrino. After some time, we see some muon neutrino.
No, I mean left-handed neutrinos, sterile neutrinos. So right-handed neutrinos.
We don't know. We don't even know if they exist.
Then how do you know they have mass of exist?
If they exist, they should have. They correspond to this neutrino state. It's not something independent.
Okay.
They are related to the neutrino.
Okay.
If they exist, they will be related to this.
Okay.
I mean, I don't know. Okay. So, if you find a theory of the largest possible group is this, which is like SU2 cross U cross U, SU2 cross U1 cross U1. Now just go through like these are the generators of that. Like you should say like we did before. These are generators like SU2. These for the U1 parts.
So these are the polymers.
Yes, these are. So they transform like this. Now we define a linear combination of some of the matrices to be like this because it's more convenient to work with it.
This is very arbitrary.
No, this is not G prime. The G prime and G double prime are experimental quantities.
I mean like the other stuff, the 1 plus gamma 5 by 4.
What is that? They are a combination of this. There's a reason why we choose like that.
Yeah, but why?
Because that is what we experimentally observe.
Okay, experiment.
Yeah.
Oh.
Like this is what we experimentally observe.
Oh. That is nice.
It comes from experience.
That is nice.
Not just mathematical theory. Physics not just mathematics. Okay, so we define a linear combination of these.
Yeah.
Now we will get the electric charge to be a linear combination of these. Okay? So I'm just going to like all these exist. I'm going to write here. So due to some reason, there are enough reasons to believe both experimentally and mathematically that we don't need to consider this symmetry, this generator. So we can get rid of the 2U to a single U. So our symmetry will be U2. This U1 is not one of the U1. This is a combination of the other U. Yeah, so we will have gauge fields here, 4 of them because we have 2 here. Yeah, for SU2 is 4. So that we have 4 of them. Now, there is something called spontaneous symmetry breaking. It's happened because the universe is initially very energetic. It went here. It was energetic. When the energy decreased, there is something called spontaneous progression. Spontaneous symmetry breaking happens, which makes it the component. Like what was the U instead of like this does not have mass, right? Okay, because in gluon field it has mass. Photon field it didn't have mass. These don't have mass. Okay, but due to something like this happening, okay, this can happen. That is also mathematical study
So
of.
basically just say you are decomposing the you keep relating the type product to other.
No, it's not decomposing. It's a linear. They change the linear combination how they feel. I'm not getting into detail. These are mathematical meaning. Like something happens due to the energy decreasing in the universe. Okay, because the potential is not symmetric.
Yeah.
Okay,
Right.
the potential of the mass is not symmetric. Something like if potential is not symmetric. Symmetry, it's just a symmetry here,
Yeah.
but the symmetric point is not the minimal energy point.
Yeah, okay, that makes sense.
The hack, the Mexican hack.
Yeah, that's what I get that. That's why it's okay. Symmetry is broken, but
We will see the Lagrangian of that later.
okay.
Something like that happened. So what we today observe in the world is 2W plus minus charges, massive. We don't know how the mass is. We come to that. Z and photon. So we unified electroweak. But this is a photon and weaks. Together as a combination of this rate. This is electroweak theory. Now we are looking at how the mass comes. So this is how the Lagrangian look. Ray, you guys think this is so scary. This is not scary, okay? This is a positron interacting with a W and a neutrino. That gives a positron neutrino W vertex.
W.
Vertex.
Yeah.
That is one vertex.
Yeah.
Same. This and D.
Okay, just all the combinations.
Hermitian only.
So just all the combinations.
Huh? Yeah. These are vertices. One vertex, second vertex.
Yeah. Okay.
Third vertex is neutrino with Z and neutrino. Electron, positron, Z, neutrino.
Yeah.
Positron, Z, electrons. Like the coefficient is just math, like the GX. You don't care about it.
Okay. So why are 6 of it?
What?
Why are 6?
These are all the. This is something that is simplest invariant. Gauge invariant, Lorentz invariant.
Okay. Okay.
This is how we did it before also.
Okay. Okay.
They can derive it. They can substitute, try me.
Okay.
These are just the basic vertices.
Okay.
And this is the electron vertex.
Yeah.
QED vertex.
Right.
Now this does not have mass, right? The W weight, all of them does not have mass. But even electron does not have mass.
Yeah.
Okay, we don't know W weight have mass. We don't expect them to have mass in the sense they initially didn't have mass before the spontaneous breaking.
Right.
But we need the electron. We just need the electronic mass because we need electronic mass. If we just impose that and we need the S matrix to converge, we will get there should be a new scale of field, which will be a doublet.
Right.
Like we had a doublet before, right? We had a doublet before.
Yeah.
Like for L,
Yeah.
which corresponds to SU2L.
Yeah. Yeah.
We need a new doublet, which we call the Higgs field.
Right.
5 plus 5 0.
Why is it mass?
We'll come to that. So we have this. So if you substitute this into, we will see the charge. What is the charge of it? This will be plus charge. This will be zero charge. Is that how mathematical algebra is the end? It's the last lecture. Next is the last lecture. And if you like now, this also requires a new Lagrangian, right? Which is again invariant. This is how we look like. Now this is the famous Higgs potential or the Mexican hat potential. This is what is correspond to the spontaneous symmetry breaking. The shape of this because lambda is greater than 0.
Yeah, that makes sense.
So
What's
there are
the
two
power 5?
Huh?
What's D bar? Is that the power 5?
D. Oh, these are the new representation. We had D alpha.
Yeah.
We had a Q3 D alpha. These are Higgs D alpha. Of the SU2 group. Of this SU2 group. This SU2 group. Okay.
So. Okay, yeah, that makes sense.
The generators of this.
Yeah, that makes sense. This makes sense. You're just taking half of it.
Now this term, we can write it in this form.
Yeah.
Okay. So this is very beautiful in the 6. What do you see here? What do you see here? What are the mass terms? These are the mass terms, right? The mass is there only. The quadratic are the mass terms, right?
Right.
There is only mass for Z and W. Photon doesn't have mass. There is a no. We started with AMUs here,
Yeah.
not this AMU, the other names.
Yeah.
The combination we had here. This AMU is not here. That just vanished. Which is algebraic manipulation.
Can you go back to the slide? How did you get this cos theta sin theta technique?
The sin theta cos theta are experimental quantities, like the weak angle.
Huh?
This is something called a weak angle and it is experimental quantity.
Okay.
There's no at least now there's no mathematical way to derive it.
Okay. That's that.
This. So what do we see? There is mass for W and Z. You know photon. Again, photon doesn't have mass.
Yes.
Interesting.
Yes.
how we had it. So we started by seeing this and not understanding anything except maybe existing of some particles. Now we know what those particles does. We know that. We know the gauge group. The SU3C was for the colors, quantum chromodynamics.
Yeah.
This was for the weak. These two for weak.
Yeah.
So what is this is the gauge symmetry group of standard model particle physics.
So SU3 is for gluon and Higgs. Sorry, gluon and photon. SU2 is
No, SU3 is for gluons.
And where is it coming from?
This combination. It's coming from this combination.
Who's doing wrong?
Huh?
SU3 से आ रहा है gluons.
Yeah.
नहीं उसमें तो 9 था तुम्हें उससे
No. It was UN. We made it SU.
हाँ ये तो SU so whatever.
This has 8 gluons.
अभी के U3 मान लेते हैं U3 cross SU2 है ये. So this is U3 cross SU2.
Yeah, cross U.
U3 cross SU2 I think.
SU.
Yeah, but SU cross U is just U. Right? SU3
Oh,
cross
this.
U.
Yeah. But this corresponds to different things.
But how did we get it?
This corresponds to the left LCD part.
What is the symmetry that we are taking for Higgs? What symmetry are we using for Higgs?
Higgs is also contained in this one.
But SU2 cross U1 will be only 3 free.
No, 4. 3, 4.
Oh, that's one. Oh, because U1. That's stupid. Yes.
No, that
That makes sense.
so Higgs is not a gauge field. Higgs was not a gauge field for us.
Yeah.
Higgs didn't came from gauge
Yeah,
symmetry.
we
It came from assuming mass.
Yeah.
Mass for electron. We assumed only for electron. We got it for everything.
Yeah. But if we take consider for can we use that to get a? Can you go back? Right. One more slide. Okay. By introducing a new scalar field SU2, does that correspond? Can we make a corresponding symmetry?
Gauge.
Yeah. Can we do the corresponding gauge symmetry for the Higgs field?
I mean, you can try with any gauge. We saw gauge field. We see.
Yeah, but what happens when you try to do the gauge symmetry for SU for the Higgs field?
Can you write a paper on it?
Huh?
That is like you playing with this stuff. Having multiple papers, looking at many representations.
Okay, because everything else that you showed us had a.
The thing is, we involved gauge of electroweak.
Yeah.
We got gauge bosons, 4 gauge bosons.
Yeah.
3 weak, 1 photon.
Yeah. No, that makes sense.
You find that the electron have mass. It is not a gauge symmetry.
Yeah, but Higgs. That's sad, I guess. Okay, it's fine.
We need mass, that's what it is. Because we know they have mass. They are spinors, they have mass.
It's fine.
Okay, they should have mass. Otherwise the entire theory is
Weird.
no, it's incorrect. Inconsistent.
Yeah.
We just involve that we got the mass terms here.
Yeah. And why is that the only way? Why is that you
Oh, you're saying but the 5 plus.
yeah, why
Oh, I said choosing. Like in electrodynamics, we did something like this, right?
I'm not saying 5 plus, I'm saying no. You said that's why the only way to do this in a renormalized electroweak theory by introducing a new scalar field SU2L doublet.
Yeah, but Cupid like this. That takes days to derive it.
Oh, so it takes okay.
Like this came in 1970s.
Oh.
The others, the QFT started in 1920s, 30s,
Oh,
30s.
okay. So it takes lots of time to derive this.
30s. From 30 to 40 years, we just come with this.
Okay, so that's the only way to do it.
There are many tries to do it. This is what.
Right, I mean, was there a proof that this is the only way to do this?
Like there are, I don't know how mathematical to prove. Like there are acceptable proofs. I don't know how complete the proofs.
Okay.
There are proofs.
Okay.
I don't know if they are absolute. Like,
Okay.
maybe some more assumptions. There have been many tries. This worked.
Okay.
And we in 2012 we detected the field.
Okay.
Just the last one. We have detected everything in this.
Yes. Okay.
So we started by knowing nothing about this. We only took one thing, gauge symmetry. To that we apply Noether's theory. We did that, we got many more particles and how they interact.
But that, okay, what about the matter part, fermions? Like, how do you explain that?
We had theory of these interact with electron weak.
Yeah.
These everything these all interact with electron weak.
Yeah.
These interact with this many interact with QED.
Yeah.
Okay.
Yeah.
Just subset of all the electron weak. Okay. Now this much has colors,
Yeah.
so they interact with
You want?
QC. We studied those.
Yeah.
Studied about all these particles.
Yeah, they correct. But I mean, that is a bit unsatisfactory.
Huh? No, that's not what
I don't. Oh, how do we get? Okay, I mean I understand that these interact with them, but like how do we get that only these interact with them?
These are the only we have detected.
Okay. Oh,
There
experiment.
might be more.
Experiment.
Yeah.
Oh.
We need money, we need better particle collectors. A new one is coming in some 10 years. Something bigger than LSC connected to it is coming. I think by 40.
Okay. So it's just experimental, the fermion.
Yeah. Even initially we only knew this. We started by knowing just about electron and light.
Yeah.
Now we have this many.
Yes.
We have many. Like we had an idea of electron from J.J. Thomson, right? 100, less than 200 years. Now we have this much. This is just one decade before.
Why do we think the conceptual groups are only restricted to SU3 plus V1?
Again, why not? I don't understand.
Why do we think the conceptual groups are restricted
No,
to
like I'm saying this we know, these many only are restricted to this, like that we know.
Okay, but how? Why do we not think that? Why
There may be more for gaze problems. There may be more interactions. There may be some quantum hemodynamics in real. We don't know about it.
Okay.
This is what we know. This is never a complete theory.
Okay.
But this is the best theory that species has formed.
Okay.
We can do a lot of things with this. Like,
Yeah, like.
this is such a good theory. It understands this many particles. Where we started with only this particle. Like these particles, especially like these top, bottom, Higgs, gluon, Z boson, tau, these all come very late.
Yeah.
Few decades back.
Yes.
50 years.
Yes.
We had initially electron and muon, that's it.
Right.
And due to some momentum conservation, we thought we also have neutrons from beta decay.
Yeah.
From just knowing about these, okay, this and photon.
Yeah.
That's when we started developing the theory.
Right.
And when developing the theory happened, technology also developed, we got all of this. There may be more. We have to find it. I hope this math seemed interesting to at least some of you. If you are interested, you can work in this one. There are even millennium problems on this, on Lagrangians theory. The statement I came up today, I don't know the statement exactly. Some of about existence of some existent things. So there are open problems. I will end it with the something I always say. So a good measure of how much we know is how much we know about what we don't know. Yes and yes.